can break the silence. We can break the silence. We can break the silence.
Good morning, ladies and gentlemen, and all distinguished guests. My name is Rita. I'm your MC today. Welcome to the International Conference on Quantum Cryptography 2022. The conference is going to commence in 3 minutes. Please be seated. For the online attendees, please confirm your online meeting devices are ready for the conference. Thank you.
Right. Very good morning, or maybe good evening to some of these participants. So, welcome to the last days of QCrypt 2022. So, we'll begin the in-person session, contributor talk now. So, in this session, we have actually two contributor talks and two online talks. And the first of this will be delivered by Stefan Bowman, if I get it right. All right. So, the stage is yours, please. If you want to use the microphone. Yeah.
Good morning.
Yep.
Okay. I'll be talking about security of discrete modulated CV QKD. And this is joint work with Carlos Pascual, Victoria Wright, and Tony Athin at ICFO, and Omar Farsi at in Lyon. Now, there have been some talks already about CV QKD, but maybe a very short motivation is that QKD was first conceived as a single photon protocol, like for DB84. But then if you actually want to perform an experiment, it's really hard to create single photon states. So usually one would just use like some weak laser pulses, which can be modeled by coherent states. So some people then thought that maybe one can just use coherent states directly. And indeed, it has been shown that there are protocols, so-called CV-QPD protocols, which where alles instead of single photons and just has to send some coherent states like this. And so basically those displaced vacuum states. And there's some parameter alpha, which is a complex parameter, which is just consists of the two quadratures here. And then those states can be either chosen according to a Gaussian distribution, so this would be Gaussian modulated CVQKD, or they could be chosen from some finite set, so this would be discrete modulated CVQKD. Things I cannot go next. Maybe battery. Okay. And then, yeah, this is what Alice sends, and Bob then performs either homodyne or heterodyne measurement. Okay. And now as for the security, in the case of Gaussian modulation, security is actually quite well understood. So there one can use something which is known as Gaussian optimality, meaning that each attack without loss of generality can be Gaussian. Now for discrete modulation, security is not that well established yet. So there have been several works. One is a protocol which uses two coherent states and then combination of hetero and homodyne detection. And then what we're interested in are protocols which use four coherent states. So called 4PSK, mentioned in earlier talks. So I think. Yeah, and there have some work on collective security, including the one by Lin et al. And by Gorai et al. This was another talk. And then as for coherent attacks, so our idea was to generalize the work by Lin et al. To coherent attacks. But coherent attacks can also be shown like independently of our work by combining the two posters, 32 and 78, also at the conference. But it's like independent of our work. Okay, so now the protocol, we assume that we take four coherent states like this. So we can assume that alpha is some real number, and then the four states are placed in phase space like this. And Alice chooses randomly between those states, and Bob, in our case, performs the heterodyne measurement. And then Alice has a random variable x, take one of four values, and Bob has a continuous random variable. But then he can discretize his random variable, for example, by dividing the complex plane into those 4 sectors, and then he also gets like a discrete random variable set. Okay, and as in the work as by Lin et al., we assume that the numbers of photons in the states received by Bob are limited. Okay, and now as for the security proof, it's quite hard to explain the full proof in such short time, but one element is that we use the source replacement scheme to go from prepare and measure to an entanglement-based system. So basically, we just consider a quantum state like this. And then the idea is that we prepare n copies of such a state. Then the A system is sent via n uses of the channel, which is controlled by Eve. And then Alice measures the A prime part. And this corresponds to her just sending them some probability. And then Bob performs heterodyne measurement. And then there is parameter estimation, error correction. And if the protocol does not abort after those, we get this CQ state, which describes the raw key. So those XZ are Alice and Bob's raw key variables. And those here are different kinds of side information. And then after that, the goal is in the end to get a perfect key state or get arbitrarily close to a perfect key state, and this is achieved by a privacy amplification protocol. And it has been shown that an achievable rate can be obtained by this smooth min entropy. So here this is sets, that is Bob's raw key. And here we use a reverse reconciliation. So we consider Bob, then we've got 2 kinds of side information. One is the random number generator, which shows us which rounds are T and parameter estimation rounds. This is something which is communicated from Alice to Bob for parameter estimation. This is a measurement result, and then it's like Eve's extension from the channel. And here we separately consider error correction. Now, of course, this is a complicated quantity depending on all rounds. So what you want is to use a single round lower bound on this. And for this, the idea was to use the entropy accumulation theorem, which already was mentioned in the protocol. So here we are during the conference. So here we assume that we've got a protocol that can be described as this sequence of channels, which gives us output and side information variables. And then from those, we can get some classical run variable C, which is used for some statistical tests like parameter estimation. And that's necessary to fulfill this Markov condition, which I think was already mentioned also. Okay. And yeah, then entropy accumulation, the main point is that when it obtains a lower bound on this movement entropy, which is in terms of this single round quantity. And now we still have to compute the single round quantity. So here, this is the set of all states which are compatible with some observed distribution. And here we take some honest simulated distribution for this. And yeah, I mean, we had to decide how to define the O and S parameters without violating the Markov condition, which was a bit complicated. But in the end, we managed to find something where basically just the random number generator is side information. Everything that comes from the measurement is the output variable. And then because of this, we had to use an additional chain rule. So this is what the left is was needed for security. And that's what we actually lower bound use in the entropy accumulation. This we have to upper bound separately. Okay, now for lower bounding the single round quantity, we use the method by Lin et al., the numerical method, and this basically is based on relating this quantity to the relative entropy here, but there's a coherent version of the protocol, and that's the phased version of the coherent version of the protocol. And then those are SDP constraints, but a convex, but nonlinear objective. So this is why we have to do linearization, just as in this paper by Linvig et al. And then the dependence on P here is still in the constraint. So this is why we then take the dual problem to get a lower bound, which is affine in P. So then we did a simulation using some fiber as a channel. So we got those asymptotic bounds, and it's still somewhat preliminary, but we believe for n 10 to the 11, we can also get some non-trivial results. So for the finite case. Okay, so yeah, the summary, we used E for system module CVQKD, generalizing Lin et al. From collective to coherent attacks. We're just looking at those examples. Our next step would be to drop the photon number cutoff assumption, and we hope to use a different method to allow bound the von Neumann entropy by Brown, Farsi, and Farsi. Okay, thank you for your attention.
Right, thanks very much. Is there any questions from the audience or from online participants? Not sure. Okay. So let me ask a question then. So your protocol works by at least sending a coherent state, right?
Yes.
And then Bob somehow discretized the plane into 4 sections,
Yes.
equal sections.
Yes.
And you say that in the security proof, this somehow converts to maximum entangled states of 4 dimensions, right? Or at least
It's not really maximum entangled state of 4 dimension. It's this source replacement scheme.
Mhm.
So it's basically a state which is 4-dimensional on in any case, it's state which is, the entangled state would be like still high dimension on Bob's side, but 4-dimensional on Alice's side. So this is still the quantum state. Yeah, but it's true. After that, we do the after the measurement, and then we do discretization. So then it would be the classical random variable would be 4-dimensional on Alice and 4-dimensional on Bob's sides.
Okay, so does it generalize? So for example, if Bob is to discretize that into, 8 equal sectors, then would it then correspond to 8-dimensional maximal entanglement? For example?
Yeah, we haven't thought about, in principle, one could choose in how many sectors Bob discretizes it. And one could probably play around with those things. Also, of course, how many states Alice sends. I think in principle, one could also have a different number of sectors on Bob's side and of states sent by Alice. We haven't explored this, but might also be possible to get something interesting out of it.
Right. Is there questions or other questions? Okay, I'm not seeing any questions. Maybe it's too early here. So there's a question, I think from Ernest? He said, if I saw the slide correctly, the version of the EAT you used was the earlier version, which has difficulties with prepare measure protocols. An approach to work around this?
Exactly. The next is to show my backup slides. If I can get there.
Go back or go forward?
Go back. Exactly.
Go back.
Yeah.
This one.
Yeah, exactly. So we had exactly this problem that we have actually a prepare and measurement protocol. So if you look at the optimization problem in Lin et al., it's of this form here. But then if you look at how the constraints look like, of course, we have constraints which are of the form which we have Alice's measurement, Bob's measurement, and then equal to this distribution. This is okay with the entropy accumulation protocol, but then we of course know what Alice's marginal state looks like. So when we can add a constraint, basically saying that Alice's marginal state looks like this we know. And actually, in order to get non-trivial rates, it's necessary to add these constraints. And then the problem is that those kind of constraints are not compatible with the entropy accumulation theorem. at least not with the old version which we use. And then the idea is, instead of those constraints, to add some virtual tomography of Alice's subsystem.
Next slide.
Yeah. So basically, we have in each round a random number generator which decides if the round is used for heat generation, parameter estimation, or tomography of Alice's system. Of course, P is not more likely than the other ones, but then for large enough n. But then, in order by using this tomography measurement, we get that the constraint can be transformed into a form like this. So this gamma tom, this is some informationally complete POVM used for the tomography. So this is then compatible with the entropy accumulation theorem. And then, but because we assume that actually Alice's preparation is perfect, we see that the tomography would only fail in case of an error in the tomography, which of course happens if you don't go to large enough n's. So maybe one more slide.
Next slide.
Or maybe one more slide. Maybe next slide. And next slide. Next slide.
Well, I'm sorry, but maybe in view of the time,
Okay.
maybe we can try to answer Ernest's questions
Yeah.
on the text box. Okay.
Okay.
Okay. Let's thank Stefan, and then we move on to the next one. Okay. So the next in-person contributor talk, Andre. Yep. Okay, will be presented by Andre. Okay. Maybe I should not try. Maybe you can tell us how it should be pronounced. Okay, it's going to be an experimental talk about metropolitan free space QKD network. Okay, the stage is yours.
Yeah, thank you very much. So hello everyone, my name is Andrej Kržić, and I work as a research assistant at the Fraunhofer Institute for Applied Optics and Precision Engineering. We're originated in Germany, and we're a rather new player in the field. So today I would like to present to you our recent work we have done towards practical metropolitan free space quantum key distribution networks. So I'm pretty sure I don't need to go into explaining you the QKD. So let's maybe just begin with a statement that now we are already, after about 4 decades of development, we're already in the phase where we are looking towards large-scale QKD networks. And in the more applied spectrum of the field, we are currently focusing on trying to achieve higher key rates, scalability, to improve scalability, and also, for example, to achieve round-the-clock availability if such systems are ever to become a commercial reality. So what we could say is that for very long distances, free space links via satellite seem to be the most feasible option. Now I have to admit that this slide needs a little bit of an update after the talks I've seen this week. But still, in general, for very long distances, say about 1,000 kilometers, at least currently, satellites seem to be the only option. Well, for metropolitan areas, typically fibers seem to be a very, very convenient option, and they are typically preferred. But there's a problem. So under some circumstances, fiber infrastructure might not be available. And a very, very obvious alternative in that case is to just use free space as our channel. But free space approach is still far less developed than their fiber-based counterparts. So we have to put in much more efforts to actually achieve QKD. I will be focusing today on entanglement-based approach, where the idea is that we have an entangled photon source, and it would be acting like a server. So we would put it somewhere in a central high-rise building in a city, where it would then stream entangled photons towards users on the other side of the free space links. Just a note here that this is not incompatible with fiber infrastructure. We could, of course, have also fiber links connected to that entanglement server. And the reason why we are So the reason why we are going for entanglement is because it offers some unique advantages. I will not go into the details here, but just maybe to mention one very important one is that simply via relatively straightforward multiplexing, we could achieve a fully connected mesh of pairwise connected users. This was already shown to work pretty well in fibers, and we are aiming to achieve that also in free space. Yeah, so when it comes to free space and we want to achieve 24/7 availability, we come to a very particular problem, which is sunlight. So whenever we try to do QKD during the day, what happens is that sunlight gets scattered in the atmosphere, and then the scattered photons enter the field of view of our receiver system, and this can pollute our quantum channel. So if we do some back of the envelope calculation just about what kind of rates we expect here, we see that we could talk about many orders of magnitude higher contribution of daylight noise as compared to the signal levels that we are dealing with, which means that we need to employ strong filtering in several degrees of freedom, namely in all degrees of freedom that we can. So first of all, we have temporal filtering, and in entanglement-based systems, this is quite conveniently implemented by coincidence-based detection. Secondly, there is spectral filtering, which is even more straightforward. We usually just employ some off-the-shelf components like interference filters. There's also more exotic methods, but usually we're limited by the spectral bandwidth of the source anyway. And third of all, there's spatial filtering, and this one turns out to be the most challenging one. So what we're trying to do is to reduce the intrinsic field of view of the telescope by putting a very tiny little pinhole into the focal plane of our telescope. But there's another problem that the atmosphere creates, which is it distorts our phase of the wavefronts, and this makes it very difficult to focus the signal, and hence it limits the efficiency. It limits the size of the spatial filtering that we can employ. So just a very brief dive into the state of the art. So if we limit ourselves only to entanglement-based systems that were performed in free space and over metropolitan distances, say less than 20 kilometers or so, what we see is that there's actually not that many of successful experiments, definitely substantially fewer than in comparison to prepare and measure. And another thing I would like to point out here is that only one so far has been reported to be done during daylight. So this was about 300 bits per second achieved over a distance of 350 meters. Okay, so how have we tried to tackle this issue at our institute? So we first developed quite versatile free space terminals. So we're planning to use these for a couple of other experiments too, not just the one I'm showing here. But I would like to just point out one main feature of this telescope, which is quite a high efficiency. And we achieved that by having very large primary aperture, which is 200 millimeters in diameter, and having no central obstruction, which is thanks to the off-axis mirror-based design. And moreover, we integrated a beam stabilization subsystem, which basically was fighting the atmospheric turbulence and tried to stabilize the beam so that we could perform the spatial filtering. So then we established a link over 1.7 kilometers in Jena, Germany, so between our institute and a container on a roof of a public service building, and tried to perform QKD. So for more details on the system, please just refer to the conference paper stated down there. As for the QKD architecture, we went for BBM92 protocol. We used an entangled photon source at 810 nanometers. And one of the photons was directly sent towards ALICE, where it was analyzed and detected, and then post-processing was performed. While the other one, well, just a note here. So the detection and post-processing is just the most typical block diagram you could expect here. So I'm not going to go into the details. The other the other photon of the pair was then sent via the free space terminals to Bob, where we hang Bob's polarization analysis module directly onto the terminal. And we had to integrate additional, as I already mentioned, spectral and spatial filtering there. We also had a classical communication channel with commercial antennas mounted in the sites, where, just as a reminder, the temporal filtering was basically achieved. And this brings me to the results. So we then try to do QKD in various conditions. First of all, I would like you to focus on the last of the three that we're showing here. This was done in the nighttime, just to show what's kind of the benchmark performance of our system. So this is the best we could do. There was no or negligible level of noise, and we achieved about 6 kilobits per second of secure key rate, with error rates being below 2%. And it was a relatively stable operation. Then, if you look at the first plot there, we did experiment during the day, but it was a very cloudy day. And you can see that on a cloudy day, despite the fact that the noise levels were much higher than during the night, we achieved basically, or very close to benchmark performance. But I think the most interesting one of these is the middle plot, which was done the day after, when the day started with completely sunny conditions. So there was no clouds, and you see that we still achieved kilobits per second rates. Even at the point when it was the brightest of that day, we achieved more than 2 kilobits per second rate. So maybe another interesting point here is that you can see very nicely how the secure key rate and the error rate correspond to the brightness level. So the background of the plots here corresponds to the solar radiation, which was measured via by a weather station, and you can see as the solar radiation increases, the key goes down, and vice versa. Yeah, just a note here, you might have asked yourself, this last drop has nothing to do with daylight. This was just an unfortunate sudden drop in performance of our entangled photon source. And just a very quick note on what kind of signal levels and noise levels we were talking about here. So at the worst time, we had a bit over 400,000 of noise clicks per second. Despite all the filtering that we employed. You can, for those who are interested, we have here the filtering parameters that were finally used. For comparison, the signal levels were in the level of about 100,000 per second. And here you can also see how the noise very nicely corresponds to the measured solar radiation. So measured with a completely independent measurement, right? So they pretty nicely match. So that brings me to the conclusion slide. So yeah, free space links seem to be a viable alternative for metropolitan scale QKD networks. Entanglement-based solution seems to be a particularly attractive approach. And we demonstrated kilobit secure key rates over a 1.7 kilometer link in night and day, which shows potential for 24/7 availability. And it's an order of magnitude improvement with respect to state of the art. So with this, I would like to thank everyone for your attention. I would also just like to acknowledge my team. Unfortunately, I can't name everyone who contributed to this project, but Uday, Sakshi, Christopher, Sebastian, Matthias, and our group leader, Fabian Steinlechner, definitely deserve a special mention. So yeah, for more details, please refer to our archive paper or watch the longer version online. So thank you very much again.
Thank you. Is there any questions from the audience? Or coming from online participants? Yeah, it seems like there's a question here. So the question is, why do you use entangle-based QKD rather than decoy state with coherent pulse QKD in your setup?
So, as I already mentioned, the entanglement-based approach offers certain advantages, and one of them I already mentioned is that in the long run we would like to do multi-user communication, and via multiplexing we aim to achieve that each pair of users on the network would achieve an entangled pair to use for encryption. Secondly, another advantage is that the source is kind of in between, so this offers a practical advantage that it can act as a relay. So the two users don't need to really see each other to communicate, right? And there's other maybe more subtle advantages that, for example, as we have seen, it has a potential for untrustworthiness. So we wouldn't in principle need to trust the source, so it could act as a untrusted node. So that's just to name a few.
So there's a follow-up also from Hoi Kwong. Why not use MDI QKD with detectors in the middle instead?
Well, it's a very good question. Yeah. So we had to start somewhere, and okay, maybe another good point here is that our institute does have a bit more experience, let's say, in developing quantum entangled sources.
Okay.
So that's, I think, the main reason.
Okay, there was a question that I missed. Could you bring it up again? Yep. So what's the generation rate of the source?
Yeah. So if we're talking about the intrinsic rates here, so let's say this is before any losses are applied, we were having about, if I remember correctly, about 10 million pairs per second. So I think it was close to the optimal rate. Yeah.
And for beam stabilization with fast steering mirror, what was the operation speed?
Yeah, so the loop speed was somewhere between, so the feedback loop speed was somewhere between 100 and 200 hertz, which turned out to be sufficient for atmosphere. So atmospheric turbulence usually acts with time scales of, let's say, 100 milliseconds. So it turned out to be just enough.
Okay, so I have one question myself. The choice of the frequency, was there any specific reason for that, or was it just the only available laser sources around, or was it less sensitive to atmospheric turbulence and so on?
So you mean for the signal?
Yeah, the 810.
Yeah, so what we are mostly looking at is either something around 800 or something around 1550, and the reason for 800 was because then we could go for highly efficient spot detectors.
I see. Okay. All right. Is there any last questions from anywhere? Okay, I'm not seeing any from on-site participants. I think there's also none from the online participants. So let's thank Andre, and we move on to the next talk.
Thank you,
Okay,
Andrea.
thanks very much. So the next talk will be presented online by Kaushik Chakraborty. I'm not sure if I pronounce it right. If not,
it's fine.
So you have 6 + 4 minutes for the talk, and if you're ready, then the stage is yours.
Okay, thanks. So I think you can see my screen. So hi, yeah, I'm Kaushik, so from the University of Edinburgh. So this talk is about like how to secure the classical physical unclonable function using quantum communication and something called a lockdown technique or quantum lock. So this work has been done in collaboration with Mina Dosti, Yao Ma, Chirag Wadhova, Meto Arapines, and Ilham Kashafi from the University of Edinburgh. So let's have a look. So what is a physical unclonable function? So physical unclonable function is a hardware assumption, which arises from the from some kind of manufacturing process of integrated circuit chips. So in IC industry, it's quite well known that due to some kind of uncontrollable and nanoscale process variations, it's difficult to make 2 chips like IC chips with a unique like with the same behavior. And so whenever we prepare two IC chips, like they have like a very unique input-output behavior, and this kind of unique input-output behavior gives them like some kind of hardware fingerprint. And as a cryptographer, we can use that hardware fingerprint to generate keys on the cryptographic keys on the fly. I'm not going into the details of these applications of the PUF. Like there are plenty of applications. Among them is like we are mostly interested in something called PUF-based authentication. So it's a server client-based setup where the server wants to authenticate the client. And before starting the protocol, what the server does, like server buys this PUF and put this PUF device inside the authenticating device, and then send some challenge to the PUF or input to the PUF and get the response, and make a challenge response database on its side. And once this is done, then send this entire device to the client. And later, if the server wants to authenticate the client, what it does, like it picks a random challenge from the database, send it to the client, and the client feeds the data challenge to the PUF device, gets the response, and send it back to the server. And then the server checks whether the received response is the same as the stored response. If they're the same, then the server authenticates the client. Because of that hardware assumption, server knows that only the specific PUF device can produce that specific response corresponding to that challenge. If the responses they are not the same, then the server says the authentication fails. And after the authentication, what the server does, like it removes those challenge response from the database, and then later it uses a fresh challenge for the next round of authentication. So that means like one weakness of this kind of classical path is that if the server wants to authenticate the client for a longer period of time, then it needs to store a huge database of a huge size. But other than that, like the very important criticism or weakness of the all the existing classical path is related to its security. So, so what happens like when the server verifying server talks to the original path, and that means it sends to the some challenge to the classical path and receives the response. Then there could be some passive eavesdropper who can listen to those challenge response pair and feed those challenge response pairs to some machine learning algorithm to model the behavior input output behavior of that path. So that means like although the adversary cannot create a physical copy of that device, but it can make like a very nice input output model. And then later when the server sends the challenge, it can intercept the challenge, feed it to that model path, and then send it back to the server. And for the server, by looking at the input output behavior, it's almost impossible to distinguish whether it's coming from the original path or this kind of model path. And this is a very important attack for the path and for the classical path, and all the existing classical paths are vulnerable to this kind of attack. So here in this work, actually, we propose like, okay, for the first time, like how to protect this kind of classical path using quantum communication. So before going to the details of a more complex architecture called the HL path, we give a very small, like simple construction. It's called hybrid path. Here, what we do, we use the classical path as a subroutine, and we feed we take the input. This hybrid path takes the classical bits as an input. It feeds to the classical path, gets the outcome of the classical path, and then we hide the outcome of the classical path inside a quantum state. So we make like out of the entire outcome, we make some pairs of classical bits, and we use each of the pair and encode them into a BB84 state. We can use the first bit to choose the basis and the second bit to choose the state. And now the adversary has the access to the classical input and the quantum output. And as the adversary beforehand doesn't know, like intuitively doesn't know what's the outcome of the classical path, it doesn't know in which basis to measure, and then it will not be able to extract the outcome of the classical path, and then hence we can claim that it's secure. But actually, so this kind of naive idea doesn't work. Like if you want to make this kind of path secure against any general adversary, we need to apply something called lockdown technique. So how does this lockdown technique based authentication works? Like it looks like this. So on the left hand side we have the server, and on the right hand side we have the client, which has this HL path. This hybrid lockdown path, and when the server wants to authenticate the client, what it does, like it has this chooses this challenge and it has this response, and it divides the response into two parts, like f1x and f2x. When it sends the instead of sending only the classical challenge, what it sends, like it also sends encode the f1x into a BB84 state, again using the same technique, and send this to client. And when the client receives this x and some rho tilde f1 of x, it first checks whether this rho tilde f1 of x is consistent with the f1 of x. That it can compute using the classical path inside this HL path. If this authentication process, that means like before giving any kind of answer, the first the client checks whether it's coming from a legitimate server. If this authentication fails, then it's about the protocol. If it passes, then it actually encodes the f2x into again those BB84 state and send it back to the server. And then server, when it receives this psi f2 of x, it also checks whether this is consistent with the f2 of x or not. And how does it work? Like I'm not going to the details, so I refer to the longer version of the talk or like our archived version of the paper. And we show that, okay, if we have this kind of lockdown, the both way authentication mechanism, then we can make this kind of underlying insecure classical path secure, just using this quantum communication and this kind of both way authentication. And moreover, like what we also observed, that because of the quantum communication, if both of those authentication process succeeds, that means server authenticates the client and the client also authenticates the server, then the adversary will get almost zero information about the outcome of the classical path. So that means like you can reuse that same challenge. I mean, the server can reuse the same challenge again and again, like when multiple times. That means like we can perform this client-based authentication using a very small size of database. Which is not possible in the classical setting. And also another thing is that like any attempt made by the adversary to extract the outcome of the classical path will result some kind of authentication failure. So that also gives some kind of cheat sensitivity. So later at the end, like we instantiate those hybrid lockdown path using something called arbiter puff, off-the-shelf classical puff, which has like 64-bit input and 2-bit output. And then here you see like the blue line actually shows the attacking complexity for the classical puff. So on the y-axis you have this modeling probability, on the x-axis we have number of samples you need. The red one actually shows the attack complexity for the hybrid puff, and the green one it shows the attack complexity of the lockdown puff. And okay, eventually you can break also this hybrid lockdown puff, but the thing is that for each of those points in this green line actually shows the authentication failure. So when the authentication passes, then you know like okay, so the adversary gets no information, so it cannot break. So that means like out of, for example, after this 200 in this protocol, actually HL puff based authentication, we can say that after 200,000 authentication failure, then the adversary can break the HL puff. Where in classical setting, you cannot say this kind of statement. And you can even increase the gap between the classical and the quantum by just increasing the input parameter, or you can go to like more sophisticated encoding, like instead of encode the outcome of the classical puff into BB84 state, you can go to like higher dimensional encoding like MUB, mutually unbiased basis. So then you can get like a higher security. So for the detailed version of these things, we refer to the archive version and also the or like YouTube talk. Thanks for joining.
Okay, thanks very much. Is there any questions from the audience? I think we have time to take maybe one quick question.
Please raise your hand if you have questions.
Not seeing anything from the Q&A. Okay, maybe let me just ask one quick one. So is there any plan to have this implemented in the near future?
Yes. So we are actually working on this, like the practical implementation of this, and also we observe that this kind of protocol also can have very high noise tolerance. So we are working on those things. Yes.
So we should see something concrete.
Yes.
Okay.
Yeah.
The next
in a couple of months, maybe 2-3 months.
Okay, is there any questions? Okay, if not, let's thank Kaushik again. So we move on to the last talk of the session.
Thank you, Kaushik.
Thank you.
So that's going to be presented by you.
Yes.
Right. Okay. Okay. Yours, you have 6 + 4 minutes. Okay.
Okay, can you see my screen?
Yes.
Wonderful. Okay, so this talk is on constructive post-quantum reduction. This is joint work with Neil Bitansky and Zvika Bratilsky, and the slides are due to them mainly. Okay, so our goal here is to lift cryptography to the post-quantum setting. So what do we mean? We consider just classical protocols or classical cryptographic schemes, but now we want them to be secure even if the adversary is quantum. So now that we have quantum adversaries, we need to really kind of rethink cryptography. So what do I mean? So first of all, we need to think about the assumptions, right? And before we could use factoring and so on, now we need to rely on assumptions that are post-quantum secure, such as lattice-based assumptions. That's kind of the first thing that comes to mind. Second thing, even the way we define security needs to change. For example, in signatures, right? Classical, we allow the adversary classical oracle access to the signing algorithm. Now, in the quantum setting, we may want to allow quantum access to the oracle. So the interface of the adversary needs to be kind of rethought. But the focus of this talk is on the reductions. So when we prove, or in the proofs of security, so when we prove security in the classical setting, does the proof carry over to the post-quantum setting? Or does it carry over to the case where the adversary is quantum? So for example, we know that one-way functions imply pseudorandom generators. Is that also true in the assuming our adversaries are quantum? That's kind of the question we want to ask. So our focus here is actually on security reductions, right? So for example, we want to solve a problem P, let's say build a PRG, a certain generator, assuming a one-way function, so assuming some assumption Q. And usually the way we prove that, the PRG is secure is we say, if there exists an adversary that breaks the PRG, then there's a reduction that can use this adversary to break the one-way function. This is how kind of the bread and butter of classical cryptography. And now the question, does this work in the post-quantum setting? And intuitively it should, because the reduction uses, most of our reductions are black box reductions. That's going to be the focus of this talk, black box reductions. And this reduction, they don't care what the adversary looks like, they use them in a black box. So why not it be quantum? So that's our question. Can these black box reductions be lifted to the post-quantum regime? And as I said, since most of them are black box and that's the focus of this, why not? They don't care what the adversary looks like. So the first thing we notice, or that people already noticed way before us, is that actually it is problematic in the interactive setting. Why? If the adversary, if the problem P is an interactive problem, then what happens if the adversary interacts with this primitive in an interactive way, then the reduction will use the adversary in an interactive way. And typically, the way these reductions work is they rewind the adversary. Now, once you rewind the adversary, we disturb the state. And this disturbance does not happen in the classical setting. And this is exactly where the security proofs break down. Okay, so we know actually that in the interactive setting, we cannot necessarily lift these proofs of security to the post-quantum setting. This we know. So the focus of this work is to try to lift these reductions to the post-quantum setting for non-interactive primitives. Okay, so for example, a PRG, pseudonym generator. I want to put security of a PRG. Okay, I have an adversary that breaks a PRG. I want to use him to break the one-way function. Can I do that if this adversary is quantum? Okay, so now it seems like, sure, why not? There's no interaction going on. Why can't we just, it should be any adversary should work. And indeed, I think many people, perhaps many of you in the audience, think that, yeah, that should work. So here's the problem. The issue why this is problematic is that the adversary may have auxiliary input. Now, where does this auxiliary input come from? Well, who knows? There can be expensive pre-processing, that gave this auxiliary input. It can be some intermediate stage from another protocol. It can be anything. But the point is, similarly to classical adversaries, which we model as non-uniform, also quantum adversary we model as non-uniform, and they may have a quantum state. Now, the problem is, if the reduction runs the adversary many times, we're back in square one in the original problem that this quantum state is destroyed or disturbed. Not destroyed, but at least disturbed. So you run the adversary once, when you want to run him again, then the quantum state is different. It may not work anymore. So that's the problem. Now, a natural solution could be, what's the problem? Just copy the state. So if you had the adversary many times with many, many copies of psi, of the quantum state psi, then it would work actually. It would work. Okay, the reduction would succeed in breaking the one-way function or the underlying assumption. The problem is that this is not constructive. Such a reduction is a non-constructive reduction because cloning quantum states is impossible. Okay, so what we want a constructive reduction. We want to say that if I have an adversary that breaks my problem using some auxiliary input, psi, then the reduction with the same auxiliary input can use A to break the underlying assumption Q. This is what we want. Okay, because we want this win-win situation that we all love in cryptography, that if the scheme is broken, at least we have an explicit algorithmic advancement. That's kind of the goal. Another goal that we want, which is relevant in the quantum setting and doesn't come up in the classical setting, is that we want durability. We want to say that if A breaks problem P, then R can break problem Q over and over again. So R can be used. So with this state, we can break LWE many, many times, not just have one break of LWE and then the state is destroyed. So we want constructiveness and we want durability. And this is, okay, so this is what we get. We get this for a large class of classical reductions. Namely, we take a large class of classical reductions and show how we can lift them to the post-quantum setting. What is this large class of reductions? These are black box reduction. They need to be non-adaptive, namely the queries that the reduction makes to the adversary don't depend on the adversary's answers. Okay, most reductions we could think of are non-adaptive, but the real issue is that it only works for decisional assumptions, not for search search. So it only works if the problem P is decision assumption, like a PRG, or if it has it can be a search, but then with very few solutions in addition. Okay, and if the reduction is of this form, satisfies these three properties, then we can show how to slightly change it or to lift it to post-quantum. Okay, to one that works in the post-quantum setting, namely it works even if its adversary is quantum and it's constructive and it's durable. Namely, it can be used to break the assumption Q over and over again. Okay, and just a line on the techniques, we essentially, the way, as an intermediate kind of on the way to get this lifting, we consider kind of intermediate models that are of interest also in the classical setting. We consider models of kind of stateful adversaries, and this is something that also is interesting in the classical setting. Okay, and let me just end by saying that why are we only stuck at decisional assumptions? Because we have a negative result that shows this is inherent. If you want, we have kind of an example of a search assumption that cannot be lifted. Okay, so I'm going to end here. Thank you very much.
Thanks very much. I think we only have time for one quick question. Do we have any questions from either the online or on-site participants? Okay, maybe let me just ask one question. So, so do we now have a good idea of I don't know how I should put it, complete classifications of what circumstances we could have these reductions or not?
Exactly, yes. So we know it, okay, it's not a complete because we know we can do it for all a decisional assumptions. We have examples of search assumptions for which it cannot be done. But maybe there are some subclass of search assumptions that we can lift. Okay, we cannot lift all search assumptions, but maybe there's some search assumptions that are liftable and that I don't know. In addition, I think it's still very interesting. So that's one very interesting question. And another very interesting question is still to think about the interactive setting. Now, of course, in the interactive setting it's much more complicated and there's many more walls we hit, but still there may be some interactive settings, some properties that will allow us to, to lift, to do some kind of rewinding in some settings. So this is kind of a first work in this area. I think there's much more open questions here than, closed ones. So, yeah.
Okay, great. Okay, so I think that concludes this session. So let's thank all the speakers from these sessions again.
Thank you very much.
Thank you for sharing.
Okay, so I guess we move on to a break or something like that.
Okay, thank you. Thanks to all of the professionals and thanks to all of the ladies and gentlemen who participated in this conference. And actually, this is a very precious opportunity to have all of the professionals in this conference in QCrypt 2022. So I would like to invite all of the participants online. Please turn on your camera. Let's have a group photo together. So all the participants online, please turn on your camera and let's have a group photo together. And I would like to invite all of the participants in this room, come forward on the stage and let's have a group photo together. to record this remarkable moment of QCrypt 2022. So all of the participants online, please turn on your camera and let's have a photo together. And all of the participants in the room, please come forward, come on the stage, and let's have a picture together. And in this conference that we have a lot of professionals and also a lot of many valuable contributors and invited talks and high quality research presentation in this conference. So thank you for your support and your sharing and your participation in this conference. So please, all of the professionals, please come forward, come on the stage, and please leave the middle aside. Please stand aside, please, because we are going to have the photo together with the participants online too. So please stand aside on the stage. Yeah, thank you all for coming, and thank you all for your sharing. And okay. Okay, so please look into the camera, and for a second, can you please just take off the mask for a camera, for a photo? Yeah, thank you. Okay. Okay, please come forward a bit. All of the online participants, please turn on the camera, and smile to our photographer. Okay, please come forward and look into the camera. 再上一点. Okay, please look into the camera and cheese. Okay, one more picture. Thank you very much for your participation. Thank you. And could we just give applause to our Professor Liang for leading this section? Thank you. Thanks, Professor Liang. And also thanks to all the audience, all the participants who participated in this conference from this section. And in the next section, we will have another section chair to lead the last section of QCrypt 2022. And now we are going to have a 30 minutes coffee break. Please take a break and come back at 10:45 Taipei time to participate in the last section of the conference. Thank you.